This is going to be part 5 of the video lectures on Chapter 2 of Fluid Statics, which stands in for class lecture number 4. And we're going to start talking about hydrostatic forces on submerged surfaces. So in the last lecture, we derived the fact that pressure acts isotropically. That is, it is a scalar. It has no direction associated with its magnitude. Additionally, we derived that pressure varies linearly with depth under the effect of gravitational acceleration, or more generally, that when a fluid element is subjected to a body force, such as that caused by gravity or a similar field, like a magnetic field, pressure varies linearly in opposition to that body force in order that it constantly negates the effect of that body force. That is, the surface forces negate the body force. And from that fact, we derived that if you take a point with a known pressure, such as one along the free surface here, then you can simply equate the pressure at some depth, known depth h below that, or let's go ahead and use what's already drawn here. If we have a known pressure P2 up here, then the distance, or then integrating the known dp dz, that being equal to the gravitational specific weight, through this distance z2 to z1 gives us a distance h, and the pressure at 1 is simply equal to pressure at 2 plus rho gh, shown here. Okay, so we extended that concept into that of manometry, and hopefully you went ahead and did some of the supplementary reading on different types of manometers, but the gist of it was that for a fluid called a gauge fluid with a known specific weight or known density, then the gauge pressure, or the pressure of one point relative to the atmospheric or reference pressure, can be read or equated simply to the difference in the height of column, or the column height of the fluid on two different branches of the manometer. Okay, so we're going to continue to extend this concept of static pressure fields into the forces that they induce on bodies or surfaces that are submerged in fluids. So this is what makes ships float, dams collapse, and submarines implode. All has to do with static pressure. So we're going to go ahead and go through this process through a couple example cases, and I'll be splitting each example case up into a separate little video module so you can watch them separately. The first one we're going to consider is the case of a tank made up of planar surfaces like this, with a horizontal bottom and vertical walls. And what we're going to do is compute the pressure acting, the resultant pressure, and the location of the resultant pressure on each of these surfaces. So if there's a pressure acting uniformly over a surface, you can turn that into a resultant force and calculate the location of that resultant force. Shown here. Same idea as you've probably used in your statics courses, where a group of forces can be collectively represented as a single force at a different location. Similarly, on the vertical walls, we're going to compute the resultant force and its location as well. Okay. So let's consider the case of, let me go ahead and make this gridded so I can draw more neatly. So let's consider a tank. I keep coming back to this tank of liquid. It's because it's really useful. And we'll give this tank a free surface. And we'll go ahead and define a coordinate system at the intersection of the free surface and this wall, where this is y and this is z. This means that according to the right-hand rule, x will be pointing out the page at us, such that the tank could be drawn, as it is a section of a three-dimensional tank that is going normal to the page. So the first task at hand is to compute the force acting on the bottom of this tank. Okay, so let's go ahead and define a few more quantities. We're going to go ahead and say that L, let me erase these. L is the length of the tank. H is the depth of the water. And W is equal to the width of the tank measured along the x-axis, which is normal or orthogonal to the page that is going into the paper. Okay, so I'm going to go ahead and borrow a screen clipping of this tank. So I can put it in the corner. Oh, that did not work. Sorry, bear with me, guys. There we go. Okay, so we've got our picture of our tank here. That didn't want to stay on top. So, question A. What is the pressure on the bottom of the tank? So the pressure at the tank bottom. So this should be fairly easy. We know the specific gravity of the fluid, gamma. We know how deep the fluid is. And we just learned in the last video lectures how to compute static pressure fields. So hopefully you're already ahead of me and have it written down that P at the bottom is equal to P atmospheric plus rho g h. Good. Note that in the drawing in the upper right hand corner here, we're being instructed to ignore the atmospheric pressure. That is, the pressure at the free surface is equal to 0. And I'll get into this a little more later. But for now, let's go ahead and say that this goes to 0, meaning that P bottom is simply equal to rho g h. Why? Because we know the pressure at the free surface. We know it varies linearly in the vertical direction. And we integrate along h, giving us this value. If that doesn't make sense, go back and review the book and the previous lectures until it does. Or come visit me during office hours once I return from California. So, next question. We'll say B. Force on the tank bottom. That is, what force does this pressure exert? So, as you probably know, as we just computed here, pressure at the bottom is simply rho gh. That is, it's constant across the entire bottom. So this is a distributed load, right? And distributed loads we account for by integration. So integration gives us F bottom well, no, let's go ahead and call it FR, since we're the magnitude of this FR, go ahead and call it the magnitude, is equal to the integral over the area of P bottom times differential area. Okay, now the question is, what do we use as this area over which we integrate? Well, we know that it is L, the bottom is L long and W wide, so this is equal to integral from 0 to L, 0 to W, P bottom times dy dx, right? Well, dx dy. And since we know what P bottom is, this in turn is equal to integral from 0 to L, 0 to W, rho gh times dx dy. Well, we just specified that rho gh, they don't vary along the x or y directions. They're not functions of either coordinate. The static pressure in this case is a function of only the vertical coordinate. So we can go ahead and move this quantity outside of the integral to give us is equal to rho gh integral from 0 to L, 0 to W, dy, dx. Hopefully you recognize that this is simply the area of the bottom, giving us rho g h L W. Now, it may seem redundant, but I'd like to point out a couple equivalencies here. Note that, oh, come on. This here is the specific gravity, and this here is the total volume of fluid in the tank. At the same time, you could say this is the pressure at the bottom, and this is the area of the bottom. Okay? So it should make hopefully some intuitive sense that the pressure acting on the bottom exerts a force equal to the weight of the volume of fluid above it. Right? You wouldn't have it any other way. So where does this resultant force act is the next question. So we're going to go ahead and make that C. Where does FR act? So the resultant force must act through a point that causes the same moment about some point in the coordinate system as the distributed pressure over the bottom. So we're going to use this using or solve for the location of FR, that is this YR location, using equivalent moments. Meaning, we're going to generalize this to vector formulation in the next segment. For now, we're going to go ahead and assume, leave the vector components out and just solve this as scalar equations. So the magnitude of the resultant force times the distance from the x-axis. So we're equating moments about the x-axis, must be equal to the integral over the area of y times df. Y times a small force gives you a small moment. Integrating all that over the area and adding up all the small forces gives you the total force. And this df is in turn equal to pressure times dA. All right? So this term here, this pressure times dA, is what we just solved what we just came up with in the preceding calculation of the resultant force. So we can go ahead and continue to write this as equals the area of y times rho g h, that's the pressure, times dA, equal to rho g h. We're moving these constant components outside of the integral, a of y dA. Okay, and finally, this means equals rho gh 0 to L, 0 to W, y, dx, dy. So this first integral, we can go ahead and move along. So rho g h, 0 to L, 0 to W. Oh, sorry. We're evaluating the first integral. Yx, evaluated at 0 and W, dy, which simply gives us rho gh, 0 to L, y, W, dy. Okay, integrating this. I know this is getting repetitive, guys, but I'm going to go through all the steps. Integrating this gives us y squared over 2 W evaluated at 0 to L, which finally plugged in gives us equals rho g h W L squared over 2. Okay? Now remember, this is the total moment, not the location of the resultant force, but this is the moment induced by the total distributed pressure. So how do we harking back to this equation right here? How do we compute this y sub r component? Well, we divide the resultant force, which we calculated in the preceding step. We divide both sides by this resultant force. And this resultant force was simply equal to rho g h L W. So let's go ahead and say y sub r is equal to this rho g h L squared over 2 W divided by rho g h L W. And remember, this is equal to Fr times YR divided by Fr, magnitudes, because these are vectors. All right, so cancellation gets rid of all these components, gets rid of the exponent there. Sorry, we're leaving the over 2. W goes away, L goes away from the denominator, leaving us simply L over 2. This also should hopefully be fairly intuitive to you. Since the force is distributed equally on all parts of the bottom, it would make sense that the force resultant occurs at the center. If we went ahead and solved this in the for the x location of the force, we would find that x sub r is simply equal to W over 2 as well. That is, it occurs at the geometric center of the bottom of the tank. Now, this is the case only when your pressure is constant, as it is in this case. So in the next little installment, we're going to go ahead and see what happens when we try to compute the resultant force and its location along one of the vertical walls of this tank.